Hey guys, welcome to Mathletics. Today I'm going to talk about eigenvalues and eigenvectors. Now let's suppose you have a matrix A, which is a 2 by 2 matrix. With some values in it. Now eigenvectors are column vectors that if multiplied by A would give us a transformation which is the same as this eigenvector being multiplied by some constant. So what I mean is, if you multiply A with a column vector x, an eigenvector, then you get the same eigenvector times a specific constant lambda, which is known as the eigenvalue. Now let me show you this a bit better. Now say you have A as 1, 1, 1, 1, and the eigenvector as 1, 1. Then, if you multiply these, you get a column vector 2, 2. So we have transformed this x to a new vector. Now, remember, each eigenvalue has a specific eigenvector associated with it, and vice versa. Note that for differential equations specifically, we will only be dealing with non-zero eigenvectors. Which are also called as non-trivial. Because trivial solutions, as in zero eigenvectors, are boring. So back to our definition. This is how we define eigenvalues and vectors. If I move this stuff to this side, I get this. Now recall, any vector multiplied by the identity matrix is the same vector. So I'm going to put this right here. Then we get A times x minus lambda I x is equal to 0. Now this can also be written as A minus lambda times I times the eigenvector is equal to 0. Now this is quite an important formula. In the expanded notation, this is A11, A12, A21, A22 minus lambda times the identity matrix, which is lambda 0, 0, lambda. Now this whole business multiplied by x equal to 0 looks like this. Recall we said that we want to deal with only non-zero eigenvectors. These are only possible if the determinant of this matrix right here is equal to 0. There we go. So our A minus lambda I is equal to A11 minus lambda, A12, A21, A22 minus lambda. So the determinant, as you know, is found by cross multiplying and subtracting. Now if you do that and you play around with the algebra a little bit, you should get lambda squared minus A11 plus A22 times lambda plus A11 A22 minus A12 A21. Looks amazing. So notice that this is also the definition of the determinant of A. And this is the definition of the trace of A. Solving this quadratic equation will give you the eigenvalues of a 2 by 2 matrix. Once you have solved for the eigenvalues, you can go ahead and solve for the eigenvectors, which you do by plugging in the eigenvalues into this equation, which we have already seen. You will use row operations to get linear equations, which I'm pretty sure you know how to solve. Say we have, I'm going to show you an example. A is equal to 1, 1, 1, 1. And we want to find the eigenvalues and the eigenvectors. Step number 1 is to find this matrix. So it's 1, 1, 1, 1 minus lambda 0, 0, lambda. This is A and this is lambda I. Now this is 1 minus lambda 0, sorry, not 0, 1, 1, 1 minus lambda. Next, you will find the determinant of this matrix and equate it to 0. This will make sure that our eigenvectors are non-trivial and that we get our eigenvalues. You can either perform row operations or just use the formula that I wrote right here. So according to this formula, we have lambda squared minus the trace of A plus, this is multiplied by lambda, plus the determinant of A is equal to 0. Now the trace of A is 1 and the determinant of A is 0. So putting these in our equations here and this here, we get lambda squared minus 2 lambda is equal to 0. And if you solve this, you should get your eigenvalues as 0 and 2. And there you go, we have solved for our eigenvalues. So now, to find the eigenvectors, you plug in these values into our formula. And you have to do this individually for each eigenvalue. So for our first one, let's take the first one to be 2. So we have a minus lambda I, which we found here. So we have 1 minus lambda and 1 minus lambda here. So 1 minus 2 is minus 1 and minus 1, and these were 1s. And now this is multiplied by x equal to 0. Performing row operations, you can see this is negative x1 plus x2 is equal to 0, or x1 is equal to x2. Let's say x2 is 1. Then x1 is also 1. So our first eigenvector is x1, x2, which is 1, 1. Repeat the same thing for lambda is equal to 0 from here. So we have a minus lambda I, again the same thing. So this will give us 1, 1, 1, 1 times x1, x2 is equal to 0. Or you can say 0, 0. So x1 plus x2 is equal to 0 from row operations. Or x1 is equal to negative x2. Let x2 equal to 1, then x1 is equal to negative 1. So we have our second eigenvector as negative 1, 1. And there you go. You have solved for 2 eigenvectors and 2 eigenvalues, and you're done. Remember, for a matrix, a square matrix, which is n by n, you will only have n number of eigenvalues and eigenvectors. So here we dealt with a matrix which was 2 by 2, so we got 2 eigenvalues and 2 eigenvectors.